Okay, sorry, let me wait a sec. I need to set my. Okay, we will get started. So, let me pull up my slides here. So, we ended. Okay, make sure that we. Yes, we'll talk about epipolar geometry today, but before that, let me continue with the camera calibration, just complete what we talked about last time. So oh, actually, yeah, I prepared some. Pull your chat also. Yes. Okay, that's good. So let's have a quick review of what we had like last time first. So we have the basically talk about the camera model and also the camera matrix. And we have, let's say, basically have some 3D points here, like 3D points in space. This is in the homogeneous coordinate. I remember that when we project to the screen there, or like project to the frame, or like project to the sensor there, if you assume that the camera coordinate and the world coordinate is already aligned, and also like if everything is perfect, like in the sense like there's no any artifact or like any imperfectness of in terms of the in the placement of the sensor or like in the manufacturing of the sensor, then it will be simply have the projection matrix or like the camera matrix is simply like this. But think of that like our camera coordinate and the world coordinate can be different. Then we need to first like project the world coordinate or align the world coordinate, or like if we have something that is in world coordinate, we'll first like convert that to camera coordinate. So here like after multiplying this, we'll convert to the camera coordinate. And that is essentially last time we argued that it's just like doing a translation. If we have a world coordinate and camera coordinate, we'll first like translate the world coordinate, the origin of the world coordinate to the camera coordinate's origin, and then I do a kind of like rotation along from the world coordinate. Maybe the world coordinate is here, camera coordinate is here. So we will kind of like rotate the world coordinate to the camera coordinate as well. That will be that rotation here. Um, and then we have like the same projection here. Like here, we instead of 1/d, we change it to 1 because we can absorb that in the intrinsic camera matrix K here. And this part, when we multiply together, is simply equal to RT, right? So this will be equal to just RM RT, and or we can write RT as a small t here. So then we have like this part we call the extrinsic camera matrix, and this is the intrinsic camera matrix. And the intrinsic one, as you can see, like I can have the scaling. At first, I can have like the camera center, or like I shouldn't say camera center. The sensor center is offset. Like if a sensor center is like right at the middle, then U0 and V0 is equal to 0. But if my origin of the sensor, like here, say now is in 2D, like after you map into the sensor, if I warp it, if I put it in here, like you see visual is here, then I need to offset that back here. So I have like the intrinsic one at the back, like you see visual here. And And then actually I probably should be use minus U0 minus V0, I think. And if like there's a different aspect ratio, like horizontally and vertically, so maybe like the unit here is like say 1 millimeter like per 1 millimeter probably is too big. Anyway, like this is like maybe 1.2 millimeter. So we can kind of like take care of that, like using this alpha here. And finally, if there's some skewing here, this skewing can be taken care of like by this S here. And if you look at the number of parameters here, like, so I have the intrinsic matrix here, have the number of parameters, say how many of them, like one here, two here, right? D is one, S here, three, four, five parameters here, right? And here, oh, by the way, like, maybe starting with a question right here. How many parameters you think here in this extrinsic matrix? This intrinsic number of parameter. Anyone else? Like, yes. Okay, yeah. Okay. So that's very good because you think of like translation, there's a in 3 dimensional, say translation have like 3 parameters, right? And rotation also, like you can model any rotation. Like let's say you can model any rotation. Let's say first rotate along the, let's say this is x-axis, y-axis, and z-axis. I can first rotate along the x-axis, say by a certain degree, like let's say theta x, and then rotate another like y, another axis like theta y by like sorry, y-axis like by another like theta degree, and also like so on, like this is by theta degree, right? So therefore, like that will be like uh six number of parameters here. So okay, is that now okay, yeah, actually last time, hopefully this time is uh hopefully it won't hang. Let me, I still like to play a demo. I have put some gap like of my laptop from the table. Hopefully I have like more air going in and then more overheat, but we'll see about that. So let me pull this one. Is that what? Is that this one? Pull this one again. So yeah, this moment of truth. Like hopefully it won't just like suddenly crash. Uh, this is a fast computer, but unfortunately, I don't know why this is so easy to overheat. Like this is like a gigabyte computer with with GPUs, but yeah, this brand it is very easy to overheat. So anyway, so this is a I have again like last time we said there's some point count here, right? So you can see here I'm showing like the transition and filters. And this is precisely the parameters in the camera matrix. But I don't have the intrinsic camera matrix here. I only have like put the extrinsic. I have the T and theta here. Theta is like the angle like for different rotation. And I have the U and V also if for the intrinsic one. Yeah, I almost have all the parameters. Just like the aspect ratio, I don't have like different aspect ratio here. And I can play around a little bit, even though it's not too obvious with the theta here because you don't know the axis here. So if I change the theta, what I'm doing is I change the theta, I change the camera matrix there, and then correspondingly, like the projection will be different, right? So let me just make sure you know what I'm talking about. So what I'm doing is basically I have the point clouds here, I have the 3D points here in space, so with different colors. So I just change the parameters inside this matrix here. And once I change the parameter in this matrix, then I have the corresponding 2D points here will be different, right? So it's showing in this different location in the screen, on the screen. So, yeah, I can play a little bit like this. I don't know, this is have an x-axis, I rotate along the x-axis, and then rotate along the y-axis. This is rotate along the z-axis. So, okay, anyway, this is maybe I should just quit this quickly. Otherwise it may overheat. So, okay. I guess I can leave this here. Let me continue with the slides here, just so I have some, I probably skip many steps, but remember last time we were talking about, wow, the fan is running high, or I don't know why. So anyway, let me take a look quickly. There's not much stuff I can queue anyway. So anyway, remember last time we saying that like, okay, for the anti-camera matrix, we didn't consider yet some kind of like radial distortion like this, because in the camera matrix model, we're based on a pinhole camera, right? So it doesn't consider, let's say if I have a lens and then the lens have distortion, like this kind of barrel distortion and pincushion distortion. So, but we can take care of that like with, say, additional coercion. Like this is like after the camera projection, let's say after the projection here, I've coordinate X and Y here. And then I can introduce some radial distortion coercion. This R here is basically the distance of your pixel in the sensor, like from the center of the sensor. So then you can do a radial distortion and you have this X and Y here. Of course, you need to figure out this K1, K2, or K3 here. So you can did that like with some calibration, you're able to find this K1, K2, and K3. So some quick word for calibration here. So as you mentioned, we have the world and the camera coordinate, right? And if you put up a camera straight away, just trying to figure out the 3D points in space, most likely you're not interested in how's the, oh, actually you can be like, actually you can assume that like the camera center is the origin, but if you have multiple cameras, you need to figure out which one is the origin, right? In any case, you may want to have a world coordinate that's different from the camera center, from the camera coordinate. So then your extrinsic matrix won't be simply identity. And so then you want to find that extrinsic matrix, and most likely you need to find the intrinsic matrix also. So, but let's say like if we use a pinhole camera model, assuming we don't have the radial distortion, like the barrel and pinch cushion distortion we mentioned earlier, then again, our common matrix is simply like this, right? And remember that like we have like 15 parameters earlier, right? We're saying that like the intrinsic common matrix have 5 parameters and the extrinsic have 6 parameters. So I have like in total like 11 degree of freedom. So actually exactly like this, because I remember that like if we have the projection in homogeneous coordinate, scaling is not a physical, it's not I mean, it's not something physical. Basically, we can scale this kind of matrix, and yet like it will represent the same point in space. So therefore, like we have like 1 degree of freedom less, so exactly would be 12 degree of freedom. So basically, we want to find the parameters here, like M11 up to M31 here, M34 here. So again, we can do exactly the same thing as before. That's why I remember what you did in your homework exercise. I guess the third one to do a least square computation like for parameters, solving the homography. This one is exactly very similar, right? So you have some coordinate is known. I have this is unknown. Then I can again I reparameterize this whole thing. Let's say if I have like this known 2D coordinate and known 3D coordinates. So here we assume we know the coordinates. If we don't know the coordinates, we cannot do calibration, right? So here we assume that we know these 3D coordinates here. And then we can just now knowing that these are the parameters, we can rearrange into a set of linear equations, right? So therefore, like we have basically, okay, basically like we have like SU is equal to this one, SU equal to this, S equal to that, and UV is equal to this one, right? And then we can rearrange the parameters here on this other side, or the variables say on the other side here. And then I basically, okay, let me just go. Basically, we have something like this, right? And remember that M1 are the variables, and X, Y, Z, and also UV are given, right? So, and therefore, like you can just form a system of equation like this, like before we have like some A is equal to 0. And remember how we solve that. We can find the single vector, or sorry, single value of the, single vector of the single value with the of the minimum single value, and that is basically the solution. I mean the single vector of A basically, and then like so. Okay, this is repeating what we talked before. So therefore we use SVD. We can solve that. We find the A here, right? So we mentioned that, okay, the last time actually we mentioned I decompose as A transpose A, find the eigenvalue for eigenvalue decomposition. Actually, we didn't talk about it as 3D, but yeah, it's okay. Okay, I don't know whether I should spend time on that, but maybe not. This is not a linear algebra class, but there's just like a quick word here. It's like the singular vector for A transpose A is basically a single, the eigenvector for A transpose A will be just a single vector of A. So therefore we can solve for a single vector for A instead. So like we decompose A with SVD like into USV transpose here, and then like find the S, find the eigenvalue, single value with the minimum single value, and the corresponding like single vector, actually more precise is the white single vector like V here. So then the V should be your solution. So and that we will find the M here. We find the corresponding M here. This is just a simple code like in MATLAB. So you just, okay, after doing single value decomposition, we pull out the V here and take the minimum eigen single vector. And yeah, I should say minimum, sorry, the single vector of the minimum single value. Here we assume it's sorted, right? I assume like if it's, yeah, if it's not sorted, then you need to sort them. So here is assuming it's already sorted. So the last one is like the one with the minimum single value. So then we pull it out, we shape that, then we get back M. So for one thing is like yeah, okay, that's it basically. And by the way, like we get we want to, let's say we want to get back like the intrinsic and intrinsic parameters here. So then we would like to decompose M matrix into this K times R and T here, right? So what we can do is like knowing that like the K matrix is a triangular matrix, and R is a rotational matrix. Therefore, it's a orthogonal, meaning that like R transpose is equal to 1. And so therefore, what we can do is like we look at just like this part here. Okay, maybe I should just write it here maybe. So what I mean is like we got like an M matrix, right? This is a K times R T here, or like I should R small t here. This is my M matrix, right? We say like this is a M matrix like M11, M12, sorry, should be M21, M2, M31, M12, and so on and so forth. Like that's M34 here, let's say. So I have this M matrix here that we computed like using calibration, let's say. And then we want to find back like this KMRT here. What we can do is say we can just pull out, let's see. Pull out like, okay, maybe I write more, like maybe more clear. M22, V2 here, 13, M23, M33, and so on and so forth. Okay. Now let me just finish the whole thing. M14, M24. Okay, let's say. Now this entire M matrix, I know the entire M matrix. Then this one I basically have like this is a 3x3, R is 3x3, this is 3x1, right? So I multiply this together. I have KR and KT here, right? So then therefore this is equal to KR, right? Now because R is a rotation matrix, basically is a orthogonal, so meaning that R transpose R is equal to identity, and K is a upper diagonal matrix, right? Sorry, upper triangular matrix, right? So actually that's you can decompose a matrix using some kind of decomposition, just in say like in MATLAB or like in Python. We have this so-called RQ factorization. Not QR is RQ, know that like we can factorize into the rotation and then like the into the upper triangular matrix and the rotation matrix. So then we can get back K, and we know what's R, so therefore like we can find T as well, right? So because so if we know K here, we know this part here is KT, then therefore like I have T is equal to K inverse multiplied by this M1 for M2 for and M3 for here. And then when I get back T and I know R as well, then I know that R big T is equal to small t here. Then I can find this big T as well. So this is just repeating what we said here. And with the T and with the R, we can find better the camera center, right? So this is just illustrating. Then we can find the camera center like in the world coordinate there. So basically, you have the calibration. You know, where is your camera? Then if you have after the calibration like in the world coordinate. So this I will skip that. Okay, let me do a quick demo. So for calibration, but for safety here, I'm thinking maybe I should shut down this. The fan is still running high. Maybe if I shut down the virtual box will help a little bit. So let me pull the code here. Calibration. Okay, it may probably is okay. So oh, I don't know why it's still running high. I need to find my calibration. Sorry, just wait a sec. Okay, so so I don't want to show myself, but I guess I have to. So this is an example. Like you see the board I'm showing here is a calibration board like that you can just download. Oops, that's why okay, yeah, that's. So so basically what it's doing is like you see like if trying to find the points in the chessboard here. There's an OpenCV, like you have a command, just find a chessboard, grid, and find all the points on the chessboard grid, and then like find that like in the screen, on the screen basically. So then if I just roughly talk about the code here, you can find this calibration code online, like yeah, I think I put it online, but also like it's like just on the OpenCV tutorial there. So you see, like I have this is just okay. The main thing here is that you see after I capture the camera here, capture the frame here, I put it in image. That's the command is I trying to find the chessboard corner here. That's the OpenCV command here, and then like so this is like trying to find the subpixel resolution because when you do calibration, you want to increase the resolution here. It's trying to like interpolate and find the corner location in this on the screen, like with subpixel resolution. This is just drawing here, but and at the same time, like I put up the location of the points here. Note that of course in the 3D space, I don't know where's the points, but I know that the points are basically basically on a plane, right? So what we can do is we can just put the point on a grid. So here is it's essentially just a grid that is just a 0, 0, 0, 1, 0, 0, 0, and so on and so forth. So each time like it will actually have a the roll coordinate is actually different each time, but I take like as you see like we took like 35 frames there, so each time the roll coordinate is different, but what we are interested in is to calibrate the intrinsic parameters there. So therefore like uh, we don't care what I mean is like we don't actually care about too much about this RT here, right? So we care about this K here. So each time like the RT will be different, but it doesn't matter. Like but the K will be the same, right? Each time we solve for the RT, which each time basically we solve the K basically with the same K, and then we take the average out, we get the K, right? And this is like essentially the K here. Let me run that like this. Um, we'll do the calibration. Okay, take a little bit computations. Wow, it's very scary, honestly, because the fan is running really high. So I should really wonder like while I'm talking. So now it's like wasting a little bit time. I don't know. My impression, it doesn't take too much time to run. I don't know why. So let's see. Did I still like have? Oh, okay. Should because I want this twice here. I didn't pay attention. So I guess I need to redo it again. So let me redo it again. So again, I just have this calibration, whatever. Like ideally, I may want to have like put the board like at different location here. So, but this is a little bit difficult. Sometimes it cannot find this chessboard pattern here. By the way, for you guys, I play with that at your home, at home. Uh, know that like I made a mistake like earlier. Last time I didn't realize that like you need to make sure that um the size of the chessboard like match with the calibration pattern like you downloaded. So from my calibration patterns, I say is 16 by 11. The board is 16 by 11, but because you're finding the corner inside the, what I mean is like, for example, like if you find the chess, if I find I have a pattern, let's say it's a, let me just randomly draw patterns here. Oh, and by the way, like your pattern, like the number of row and number of columns cannot be the same. Otherwise, it cannot orientate, don't know which is which. So that will be like some ambiguity there if you have the number of, I mean, oops. If the number of row is equal to number of column, oops. See, I'm totally sleepy. Okay. So this is a pattern of like 5 by 6, right? But note that like for the OpenCV code, like doing the calibration, is trying to find the corners, the internal corners here. So therefore, like the grid pattern that you're giving to that like should be like 4 by 5. So otherwise you won't be able to find it. For example, like if I have a bigger pattern, and if I try to look for in the past I made a mistake. Like for example, I give a pattern like 10 by 11, and I ask it to look for 5 by 6. sometimes it's able to find it, sometimes it's not able, right? Because it does not exactly match with the pattern. So okay, this is just a kind of remark to make sure you don't make the same mistakes as I did. So okay, then I should have one that like while I'm talking anyway. So yeah, it used to be that long though. So compared to calibration matrix and this matrix, it's quite consistent. You see, it's like almost the same as I did before. And you can see like the results that is trying to remove the distortion. So here, like I have some radial distortion. It's artificial because actually I put a lens here just make to exaggerate a little bit. But you see, like after remove the distortion here, is actually it's doing quite well, right? Because the line, the parallel line or the straight line is supposed to be straight line, right? So if I have the pincushion distortion or like you have the belt distortion, like the line will be curvy. And so of course, if I remove the lens now, so things will become curvy now. Yeah. So and so okay, that's basically it. A quick demo for calibration. So I guess I'm going to continue to talk about stuff I like to talk about today. So as we mentioned that I will talk about epipolar geometry. Okay, I guess I'll use the okay. That's so weird. Okay, yeah, that's good. So I will use Suno here. Simply use Suno here. Can I make it a little bit bigger even? Yeah, probably not a good idea. So okay. I probably, let's see, yeah. Okay, I guess I can do like this. So I have some space for me to draw and also like Suno. So yeah, you will see like what do we mean by epipolar geometry? Epipolar. So it's basically related to like multi-view, or actually more precisely stereo view setting. So we have like basically two views here, let's say, and these two views we try to find from the two views. Of course, all of us have two eyes, and with the two eyes, I have a little bit different. I have a slight disparity of like what we see, right? And based on the disparity there, is that this way? Yeah, displacement or like there, like we are able to reconstruct the 3D space, right? 3D environments up to certain accuracy, I guess. And that's basically epipolar geometry is the math doing that. So of course, there are lots of application. This is an example, like doing a structure of a motion, as you mentioned. So because you can think of like each of the where you have like many photos I capture for a scene. Like we can take a pair of photos at a time to try to reconstruct. At least like this would be the first solution, like basic solution we can do. Yeah, this is just another illustration. Another illustration, I guess. And yeah, we've talked about like 2D transform and like warping and so on. Like we spent some time there, and we talk about like last time and today, like from 3D coordinates into 2D coordinates with the count matrix here. So here now we're going to talk about like these epipolar geometries that we have like two different view there and trying to kind of like extract the 3D information like from two different views. And this is a very simple setup to see like how we can get the depth from disparity. And so here we assume these two like two eyes here is completely parallel. Like it's like seeing like completely in front, like they're in parallel. And note that like in general, like for example, in epipolar geometry, we don't need to set up like this. Like we can have like more general setup. So if I have a setup like this, like let's say this is the focal length here, the from the center of projection or the center of camera, from the virtual screen here, the projection plane here is F, like this is projection plane here, and the displacement like for one side is X, the other is X pi here. Then we can just say using like simple geometry here, simple trigonometry here, this two kind of triangle is kind of like similar to one another. So therefore, like we have what we have like T over C is equal to T minus XL and XL over C minus F, right? Something like this. So yeah. Or yeah, or like if I should be plus XL minus XL because here like XL is is on the negative on the negative side. So anyway, then like we arrange that, like we will get like Z is just equal to T over XL minus XL times F. So it's like if the displacement is bigger, actually it's very intuitive. It's like the displacement is bigger or the disparity is bigger, then things will be closer. If the disparity is smaller, then the objects like the point is farther away. So this is a very simple kind of like setup that we can find. But in general, like we need to go into a more complicated case because like your camera most of the time will not be as nicely aligned as like this. And also like you may not know like what's the gap, like the kind of like the displacement from the two camera center here. And this we may need to figure that out. So this like will involve this calibration, right? Previously we have the calibration is just the calibration with a single camera like here. Of course you can calibrate like each camera individually. But remember if we do calibration like what we did earlier, it will be only able to find the intrinsic matrix, but not the extrinsic matrix there. So then yeah, we need some other way to calibrate basically. And also like we have the calibration problem here, like after we calibrate the cameras, we need to find the correspondence, right? For each point in space here, we need to figure out like where this point like are located on the screen, like for the left camera and the right camera. So for example, this is an example that like if we have the image we find the disparity here, and then maybe from the disparity that we can generate the corresponding depth. Okay, it's not showing the depth. So okay, anyway. So now this is like what we're going to learn here. Like we will learn to find. Okay, I guess before that maybe like I will just say give you a little bit motivation. Like why this epipolar geometry is great. Like besides besides that, like is able to do calibration. So think of like this: like if we have remember we have these two subproblems, right? One is like I do the calibration. I want to find what's the um, what's the one camera, what's the relative location of one camera with respect to the other cameras. The other thing is I want to find after I have a scene here, I want to like extract 3D information. I want to find like for each point in the scene, like what's the corresponding location in the other scene here. So let's say here, like I have trying to look for this like garbage bin here. So for human, it's quite easy to find, okay, this is my corresponding garbage bin, right? So, but for a computer vision system, it may not be as easy. Maybe I want to find like, okay, if the garbage bin here, we want to say, instead of like looking for the entire scene, maybe we want to like refine to like restrict to, okay, just trying to look for like somewhere here. Maybe like we know that like this is like the approximate location of this bin. So we will just like trying to look for it here. Maybe even like, actually, with the epipolar geometry, it will be a little bit different. Like not you find a particular location, but if everything is calibrated, what's going on is like if I know that on one scene like I see is here, I will know that on another scene is like somewhere like lie along this line. So again, like, I can reduce the search space here significantly. Instead of like trying to search for the entire scene here, I can just search inside this strip here and try to look for this garbage bin for correspondence. So this both improve the performance or increase the speed of like running this algorithm, but at the same time, like it can improve the accuracy because I may have like something else, like another bin is looks quite similar to this one. If I search the entire space, then I may kind of like think that this one is like the actual bins, but that will be the wrong bin basically. So okay, now I'll get into like this epipolar geometry. This is like the main kind of I would say the picture that you should keep it in mind. Okay, I should pull your chat here back. So what this figure illustrates is that I have two camera center here, right? The left camera and the right camera here. I'm shooting like to the same scene here, let's say. So like this is the projection plane for the left, for the right camera, this is the projection plane for the left camera here. So I'm looking at some point, like let's say this 3D points at X in space here. So in terms of like the left camera here, for every point along this line will appear the same point here, like on the screen here, X here, right? So however, like, so therefore, like if I just have like one camera, I don't know, like, I can only know that this point is like fall on this line. I cannot get the exact 3D location here. But if I also have the information from the white camera here. So I know that like if the points ultimately is here, then like for the for the white camera, the white camera will be seeing a point here, right? And if the point is here, it will be seeing a point here, and so on and so forth. I'm using exactly like what we just described earlier. So if I know that from the right camera, sorry, from the left camera, I'm seeing a point here, then in the white camera, this point cannot be anywhere. It cannot be here and here on the projection plane on the screen of the white camera. It can only fall on this line here, right? It cannot fall on anywhere else. It can only fall on this line here. It's exactly what I'm talking about. Like it can, when we see a beam here on the left camera, it can only fall on this strip here. It cannot fall anywhere else on the screen. So then we can just look for this point in space only on this line here, right? And we call this line here an epipolar line. This is like long an epipolar line. And if I have another point here in the space, also like it will kind of like, for example, I have another point in space like somewhere. I'm very bad at sketching. So then that, yeah, I'm probably not trying to sketch. So then like it will correspond to another line here, maybe. And note that like this line will also like cause, for all this line will cause a line that correspond to the point that connect the two camera center here. So you see that there's two camera center. If I draw a line and connect them together, we'll cross through this E here, like this E and E pi here. And we call this E and E pi the epipole. And note that the epipole, all the epipolar line will always cross through this epipole here. That's okay. That's basically that how what the structures look like. It's supposed to be I have the epipolar line. Okay, again we have the epipolar line. I'm okay. Of course, similarly, if I have like some point from the white camera here, like I look at the white camera, I have the points here, then I also have like a corresponding epipolar line in the left camera. So if I just consider the white camera here, like I see a point here, if I look at the point here, and then like the corresponding points, if I try to look for that, like in the left camera, it can only fall on this epipolar line here, have a corresponding epipolar line. And by the way, like this plane here, we'll call it the epipolar plane. Basically, it's the plane that include the two epipolar lines. Epipolar plane. So okay, this is just repeating what we said here. So we have the point here. If I see it in the left camera, we can only find that as a line in the right camera. So that is the epipolar line. And similarly, if I have a point, I see like on the right camera, I can only find that point like on some line in the left camera, also like on the epipolar line on the left camera. And so this is repeating our terminology here. So and also some of the notation we are using here. We have this big axis, a 3D point in space, and the small x here at the projection to the plane on the left and right camera. And I have like this is the epipolar plane again. And the epipole is the intersection of the camera center of the other camera, the projection of all the other camera center on the screen here. Basically, if this camera, if you look at the other camera center is here, right? It project to this here, that is the epipole. We mentioned about the epipolar lines as well. So okay, hopefully it's clear. Okay. Maybe just say a quiz of like you guys are still here, and we'll see if I can go. Oh, okay. Very simple quiz. Like if you are here, like absolutely you know what's going on. So What's this line called again? So just see like anyone is still around. Oh, okay, great. Yeah, okay. So someone is still around. Yes. Uh, Now, okay, this is at the epipolar geometry here, and by the way, like depends on the camera setup. Of course, you have the epipolar lines are shown differently on the screen, and also like the epipole will be different. So, for example, like if I have like two cameras, I have this kind of rather um, kind of just like a setup like this one here. I have the white, the epipole here is still like say out of the camera here, but you see like the epipole is converging. Like this is like from the left camera, like this is seen from the left camera. If I continue to draw this epipolar line, like it should converge to some point like far away. So I have an epipolar is far away. So it's this is a kind of exaggerating. It's more like this one, I guess. It's a more it's not as what we're showing. Like it's more like this one. It's like the two field here is like more parallel. Um, and this is a two scene is like our two eyes is like just looking forward. Like they are the axis of the two cameras are basically in parallel. Um, and So in that case, of course the app you have the camera center. If you draw a line, they won't fall on the projection plane. So therefore, like you cannot see the epipole there, and basically, all the epipolar line will be in parallel. So you see the epipolar lines are in parallel, and this is another example, like another camera setup. If you have like one camera is like in front of the other camera. So if you draw the epipolar line, or like if you, as you say, if you draw the line connecting the two camera center, then the epipole will be exactly in the center of the image here. Right? Um, so now it's getting a little bit math. So I will go slowly. This is a nice math, like uh, but and also like a little bit complicated if you see it the first time, but it's not too bad. And we'll talk about basically this essential matrix and fundamental matrix. Uh, a little bit fun for like essential matrix. By the way, this is introduced in the 80s in a Nature paper, the essential matrix. The author didn't call it essential matrix. Uh, uh, this is by Luke Higgin. I don't know how to pronounce and also spell his name, Luke Higgin. But a nice remark here, like is like he's actually the advisor of like Jeffrey Hinton. Like you remember Jeffrey Hinton, like because when we talk about deep learning next time, so Jeffrey Hinton is considered kind of like the father, like seminal figure in deep learning, and his advisor is famous as well. But it's interesting, like his advisor is a psychologist, a experimental psychologist. Uh, but he introduces a essential matrix and have a very nice paper in Nature. Um, and basically, like he, okay, you see more about the essential matrix. So what essential matrix does is like, you think of like, okay, I have now I use this XL and XL here to represent the Cartesian coordinate uh, of the right and left cameras. So note that like this is like the 3D points like in space stuff. Like I'm not talking about the projection. I'm talking about like this point X here in 3D. If I look at like from the right camera and also from the left camera, if I took the coordinate system here, like of course like there will be like two different coordinates, so it will correspond to two coordinates because the coordinate systems are different. And from that one, we claim that there's some matrix E here, we call it an essential matrix, that will connect these two coordinate system in a way that like if I XL transpose multiplied by E multiplied by XL will be equal to 0. Okay, another very simple question here. What's the dimension of this E matrix here? Yes. So yeah, note that we are using Cartesian coordinate. We are not homogeneous coordinate. We'll mix the coordinate here, so be careful. Like, but this one for the essential matrix, like we are using Cartesian coordinates in 3D. So therefore, like the coordinate here is 3 by 1, right? This is like 3 by 1. So to match the dimension here, this has to be 3 by 3, right? So because like this XL transpose will be 1 by 3 here. XL is like 3 by 1 here. So this will be 3 by 3. And so we talked about this last time. And it's just like if we have like two coordinate system here, let's say I have left and right. If I want to move the right one to the left one here, what we can do is like we first do a translation. This point like this, or what I want to say is like if we have some point here in the coordinate, let's say I have some point in space here, like here, based on the coordinate system on this one here, if I want to translate into the coordinate system in the other one here, what we can do is like first we should subtract the difference here, the displacement here, and then do a rotation, and we'll get back the coordinate to this one. So the rotation will be something like a rotation like this. So as we mentioned last time, right? So therefore we have like XL here should be just equal to XL minus T, XL minus T, minus T times R here. And what we're going to claim is that like, we claim that like our essential matrix is simply, okay, before we saying that like we need to define something that you may not see that before. So I assume that all of you know cross product. You learn that like in, for example, in fields like electromagnetic. So we have like two three-dimensional vectors like U1, U2, U3, and V1, V2, V3. The cross product of like U times V here, U multiplied by V here, will be equal to determine like this. Okay, do you guys still remember something like that? Like I asked my graduate students like last week, like they don't remember this. But you should, like this is like some of this stuff I guess is very basic and it's good to remember like your entire life. Like it's, I'm also like pretty intuitive, right? So you have okay, I'm first thing first, I do make sure you're following me like what this rotation means here. So you can represent like, of course, like a 3D space or like 3D coordinates like with a vector like this. But also like I can represent like U as a U times I, U1 times I plus U2 times J plus U3 times K, something like that. So these are just the vector IJK, like unit vector, like IJK here. They are orthogonal to one another, like this is I vector, J vector, and K vector, something like that. Now, then U cross V, therefore, like will also be a vector. You look at this here, like it's I write it as a determinant. If I expand this determinant here, I get something like this way. So in terms of the I direction, I have this one here, V or J like this and K like this, right? Or I can write it back into a vector form, it will be something like this one here. So then it will be equal to something like this, right? So know that like I can I can write also this one as something like this. It can be written as the first coordinate here is equal to u3 minus v2. Minus u3 times v2 plus like u2 minus v3, right? So this one plus this one here. And so therefore I can write a matrix form multiplied by vector like this. So here we will define a matrix here. We call it like U cross here. So basically if I have a cross product, like we want to compute the cross product of a vector U cross V here, then U cross V will be just equal to this U cross matrix multiplied by V. So this is just our U cross matrix here. And this U cross matrix, note that like note that because I have U cross matrix times U is equal to all 0. So therefore, like whenever you have a matrix, let's say matrix A here, if I have AX equal to 0 and X is non-zero, it's not equal to all 0. So it's like this is X, and also X is not equal to 0, 0, 0. Then it means that like A should not be full rank, right? So if not, this is not full rank, so therefore like it should, yeah, if like A is not full rank, or like in this case like U is not full rank here, this UX is not full rank here, the rank of U should be less than equal to 2. Okay, this is just a remark, not exactly very important. So but anyway, so we have this cross matrix. We define this cross matrix here. So then like we just mentioned that we want to derive some E here, and such that like this one, the E multiplied by XL transpose and multiplied by XL should be equal to 0. And what we're going to claim is that like this E is simply equal to R times this TX here. So let's verify that. So if I have E is equal to R times TX, right? So I multiply by this XL transpose and XL. So let's see, if I multiply this XL on this side here, what do I get? Like I have T, this is TX times XL, right? So TX, remember, this is actually doing a cross product, right? A cross product of XL basically. So I'm cross product of XL, and then I do a rotation of that, right? Basically. And what is XL, by the way? XL is equal to this guy, right? So therefore, XL transpose is equal to XL minus T transpose times R transpose. And okay, kind of like another quick question here. So what is R transpose times R? R transpose times R. Yes, I think you're right, but note that they are called identity matrix, not unit matrix. So it's a 1, 1, 1. That's like basically. So note that like it's a because I Q, yes, because we mentioned that this is rotation, right? So therefore, like this is orthogonal. So we this and other things that is good to know. You yeah, it's good to know. But of course, like this is not a class on linear algebra, so I won't really kind of like spend. I guess I spend. Yeah, I probably will not now at least. So, but this R matrix I think I did spend a little bit time in the past. think of this as the rotation. Like whenever you have rotation, you're not going to change. You think of like each of the matrix you're multiplying is basically it's just a transform in a some point in space. For example, if I have like this matrix here, I multiply by x1, x2, x3 here. I multiply by this, meaning that I'm going to transform this x to some new location here. So for rotation matrix, you have this R transpose is exactly equal to the inverse R. It's basically like the R transpose will reverse the effect of R here. So therefore you have R transpose times R should be identity. Okay, this is hand waving. Okay. But okay, let's not go into that like at this moment. So yeah, but it's good to know, like good for you guys to remember that like when you have like our rotation matrix or like our orthogonal in general, orthogonal matrix, then R transpose R is equal to identity. So therefore this is gone here, this is identity. So I have what? I have like this is a T cross X, R X minus T cross X. Notice that this is just inner product, right? So I have like a vector A transpose B, let's say. This is actually just the inner product of A and B, right? So inner product of this, I get like XR inner product with like T cross XR minus inner product of T cross XR, right? So this is, I just expand this, right? This multiplied by this guy and this multiplied by this guy. Okay, I got like maybe a pause here for question. So what's this? What's XR in the product of XR and T cross XR? I guess this is a we'll finish the essential matrix, then we will continue next time maybe, but this is probably the last question here. So what was T, was XR in the product of XR and T cross XR, or like, or I may write XR transpose T cross XR here. So this okay. Remember, like in the product should always give you a scalar value. So what is the scalar value here? So if okay, maybe I should give you a reminder of what in the product. For example, I have 1, 2, 3 in the product with like a 2, 3, 4 here, right? So if I do an inner product of this one, this is equal 1, 2, 3 times 2, 3, 4, something like that. So it's like 1 times 2 plus 2 times 3 plus 3 times 4, something like this. Yes, okay. So this should be 0 because I remember like inner product also means that like if you have like two vector here, like let's say UV, the inner product of UV, what does that get? It's actually equal to U times V times cosine theta, where theta is basically the angle between the two vectors here. So therefore, if you have these two vector here orthogonal, then that will be equal to 0. And in this case here, like T times XR is like I have T here, I have XR. Note that like when you do cross product, you basically have like T cross XR is a vector like perpendicular to the plane on T and XR. So therefore, like of course T will be like kind of perpendicular to XR. So therefore, like this inner product here is equal to 0. So similar manner, like these other guys, the inner product XR, XR dot t minus t plus t equals I mean, both of them will be equal to 0. So therefore, we get 0 here. So, okay, yeah, we probably just stop here. Then we will kind of like repeat some of the stuff we talk about, and we'll finish this next time. So, and oh, yeah, and I don't know any of you guys start the last homework yet. So, maybe some quick work for the last homework is oh, I don't know whether I should spend time now. Maybe okay. If you guys don't mind, maybe I just spend a couple minutes on this one. So in case someone want to get started early, not yet early anyway, because we cannot yeah because the I know it's fun, but the class has to end eventually, so we I can't push the due date like for too long. So anyway, if you look at this one here, so what we're trying to do then for the last assignment here is we try to reconstruct some 3D points. So of course, for the scene here, if you think of like you also like have this left view and right view here, left and right. So we remember we need to do two things. So one is do calibration. So we know how the cameras are oriented. And then we need to find the correspondence here, like the points in space corresponding into two scenes here. So in this assignment, we assume that like this correspondence already done. So we don't need to care about this. So, and so I give you like a list of points like on the coordinates from the left view, and the right view, basically. And then like, and also the calibration is more or less done as well. So where is it? So oh, okay. Yeah, okay. I see like I need to go a little bit deep like to get into this. Okay, I guess I will leave it next time then. Yeah, because yeah, okay, I will leave it next time. But you can try to work on that yourself. Yeah. And especially you have the slides, my slides. If we go ahead, I have to look for the slides. And or actually you can even work on this already here. So this you can work on part 2 here, like because it's unrelated to earlier part. So here is basically saying that, okay, let's say if I have the two view here, like I have one view here and I have one view here. Now I see a point in space, right? A corresponding point in space. Here, I don't actually need to use epipolar geometry, but let's say if I know the coordinate completely, so I know where's this point here, I call it like A1, let's say I know this point is I call it like A2, let's say. And I know the vector here, say along this direction is B1, and along this direction is B2 here. So then if I need to find a point that intersected by these two lines here, so first I can parameterize these two lines here. Like one is will be like A1 plus lambda 1 B1, right? And then this another one is like A2 plus lambda 2 B2 here, right? Now, if I want to find the point of intersection, one way I can find it is simply solving a optimization problem. So basically, I want to find like A1 plus lambda 1 B1. And I subtract like A2 plus lambda 2 B2. And I want to minimize this. So this will be a vector, right? So because it is a vector, this is vector. I want to find a norm that reflect minimum lambda 1 and lambda 2. So it is quite easy here because this is a unconstrained optimization problem. So you can basically just expand this because this guy, the norm of this is just equal to A1 plus lambda 1 B1 minus A2 plus lambda 2 B2 transpose times A1 plus lambda 1 B1 minus A2 plus lambda 2 B2 here. So then to minimize this, you can just say, like in your first course in calculus, you can take the derivative, partial derivative lambda 1 set to 0, and set partial derivative lambda 2 equal to 0. So with some algebra, you can solve like for lambda 1 and lambda 2, right? So you can solve for lambda 1 and lambda 2 basically. So that's basically 2A. Actually, you can work on that already. So okay, unless you guys have more questions, I will just stop here. I will see you guys next Tuesday then.